Okay guys, welcome back to the video. Today we will take a look at the proof of Archimedean property. So let's take a look at the statement of this property. For any positive integer a and b, there exists a positive integer n such that n times a is greater than or equal to b. Okay, just try to write it in notation. For any integer a and b, positive integer, you will have or there exists a positive integer n such that n times a is greater than or equal to b. So what does it mean by this? So if you pick any two positive integer a and b, and suppose that b is greater than a, and then you will find a number that multiplying one of these number. In this case, I want to multiply a by 6. So we're gonna have 6a, which is 6 times as this one. And as you can see, the length of 6a is greater than 6b. In this case, if I pick two integer, a less than b, and then you can find a number which is 6, so you have 6a which is greater than or equal to b. Okay, that is the meaning of Archimedean property. So what does it say from this? What does it say? I think that Archimedean Archimedean no sorry Archimedean property say that a set of natural number is not bounded above. Okay, it's not bounded above. It's like you pick any two positive integer and you multiply one of the integer, then the number that is multiplied can be greater than or equal to another number. Now let's prove this property. Let's prove it. How can I prove this? For any positive integer a and b, there exists a positive integer n such that n times a greater than or equal to b. I want to use a proof by a contradiction. This means that I can assume that a Archimedean property is false. Whoa. So suppose that Archimedean property is false. Once it is false, what do we have? So we get to have the negation of this statement. So for all become for some. So it turns out to be for some a and b, which are positive integer. For some become for all, right? So it's going to be such that for all positive integer n, n times a is less than b. Okay. So right now we say that there is there are two positive integer n, and you can find any positive integer n multiplying one of the number, and then it's less than another number. Okay, interesting. So now let's have a set. So I got a let S be a set of b. I missed this step, sorry. So I gotta rewrite this one. So I gotta move NA to the right side. So we gotta have b minus NA greater than 0. okay, greater than 0. And since a, b, okay, a and b are a positive integer, okay, what does it mean? And we know that b minus na is an integer. So this implies that b minus na is a positive integer. So we gotta let S be this set, the set of b minus na, okay, where n is a positive integer. Okay, so since b minus na is a positive integer, so this set must contain positive integers. Then set S must be a subset of a set of natural number, and it must have a positive integer, so it cannot be an empty set. Okay, so if you have a subset of positive integer and this subset is not empty set, what can we use? We can use this one, well ordering principle. So it must have a minimum element in set S. Okay, so since we have this one, we can use well ordering principle. So by well ordering principle, what do we have here? We're gonna have an element x in set S such that x is less than or equal to m for every element in set S. So right now x is the minimum element in set S. This is minimum, okay, element in set S. Now when x is a minimum element in set S and S is a set containing b minus na, where n is a positive integer, what does it mean? This means that we can find a positive integer such that, okay, this means that we can find a positive integer, let's say it is k, right here, such that x becomes, in this form, b minus ka. Okay? What does it mean by this? This means that k is a positive integer such that x is a minimum element, or is the, how do I say, the least, no, is the smallest, let's say smallest, okay, smallest integer in set S. That is the meaning of having k in this case, okay, or in this context. Now, what happened next? What can we do? Right now we have x is a minimum element in set X with positive integer k. My question is, when k is a positive integer and 1 is in this set, 1 is in this set, what can we do? We gotta have k plus 1 in a positive integer. Once k plus 1 is a positive integer, it satisfies this condition. So we gotta have another element in set S. Okay? So we can have b minus k plus 1 times a in set S. And what happened next? So I'm gonna try to write b minus k plus 1 times a minus b minus ka. As we can see, this is x, which is the smallest element in set S. And then what happened? Let's find this difference. So we're gonna have b minus k plus 1 times a minus b plus ak, which is, okay, let's write it down. B minus distribute minus an a into this bracket, so we're gonna have minus ak or ka, okay, ka minus a minus b plus a. Okay, this one we cancel, so we're gonna have minus a. What is a? A is a positive integer. Minus a is now a negative integer, so it must be less than 0. From this right here, we have b minus k plus 1 times a minus the minimum element, which is b minus ak, less than 0. This means that b minus k plus 1 less than, right? B minus ka. Okay? And b minus ka is x. So we have another element which is less than x, but x is the least element, or the smallest element in set S. Okay? So this means that x equal to b minus ka, okay, is the smallest element in set S, but greater than b minus k plus 1a, which is in set S. This is a contradiction. Okay? This is a contradiction to x being the smallest element in set S. Okay? So that's what we have right here. So this means that what we suppose right here is false. So the Archimedean property is true. Therefore the Archimedean property is true. So we proved this property already. Okay? And that's the proof of Archimedean property. Okay? So that's it for this video, and see you in the next video.